Well, welcome in, everybody. Thank you for joining. Good to have you here. Get yourself ready with a notebook, grab a pencil or a pen if you're so bold. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a problem from our AP Calculus AB practice resources, again, courtesy of the University of Houston. They really want you to be successful in the AP exam over there at the University of Houston, which, hey, we appreciate that. They give us some decent resources. We'll take advantage of that. Now, the problems we're going to be doing in this series, we're going to take them one at a time. But we're starting, as you might notice, with the non-calculator section. And that's because I'm going to be able to show you some of the techniques with the non-calculator part. And then once we get to the calculator questions, we'll have more techniques in our tool belt, so to speak. So if there are any techniques that you're not completely clear on, which we might need to use in parts 1, 2, and 3, which will come after questions 4, 5, and 6. Kind of like a Star Wars thing going on here. Alrighty, so give yourself about 12 minutes on this. This is an easier type of question. 10 to 12 minutes would be a great time. Fantastic time. Give yourself that much time to work on this on your own first, and then you can go ahead and come back to this video, see how we do it here. Compare your process. Make sure to take notes during this series. If there are any last minute techniques or formulas that you're not familiar with and crystal clear with, you should get familiar with them by using these questions. These are very guided questions. I wouldn't say that they perfectly reflect the AP exam. The questions you'll get on the AP exam are likely a bit tougher than we see here, but these are great for practicing the techniques that we'll be using based on how they phrase a certain question. So let's get started. For example, when they say find the relative maxima and minima, that's telling us something, right? Let's also consider the graph in the first place. It's an even function, x to the fourth and x squared. Those are both even degree. And the graph is going to look something like, if we were to factor this out, 2x squared, x squared minus 2, which could also be written as 2x squared, x minus root 2 times x plus root 2. Okay, so this gives us an idea of what the function looks like. I'm going to have two zeros here. Of course, when x equals 0, the graph is equal to 0. And because of the even degree, both sides are going up as x gets positive. So I don't really know how far down exactly these little dips go, but I just know that they go up on both sides, and it's symmetric, okay? So this is at like negative 1.4-ish, and this is at 1.4-ish. That's the square root of 2 and negative square root of 2. Okay, decent to get an idea of what that looks like so we can keep track of the features, because the minimums and maximums, you might notice, are right here. At 0, 0, there seems to be a maximum, and then at these points, there seems to be minimum points. So how do we find maxima and minima? Right, we need to take the derivative and see when it changes sign. So we're going to look whenever f of x has a critical point. That means its derivative is 0 or undefined. We're only going to consider 0 here because it's a polynomial, so it's never going to be undefined. Let's take the derivative, shall we? So this is going to be 8x cubed minus 8x. Look at that. And we're going to factor this up, cut it up, so that we can set this equal to 0 and find what values are going to give us 0. And of course, we can get this on a good old chart to analyze. I don't think the chart is absolutely necessary here, but it's a learning opportunity. This is how you can analyze minimum and maximum behavior, by putting the factors of the derivative on a chart And we have our zeros as follows. At x equals 0, at x equals, -1, and at x equals +1. Of course, the product is 0 whenever any of these rows, which represent the factors, are 0. And as usual, the value of these is negative on the left and positive on the right of the zeros, respective zeros. So we're going to see this alternating feature, that the value of the derivative goes from negative to positive to negative to positive. So this says that it's going down and then flat and then up and then flat and then down and then flat and then up. It's literally what that says. So negative, flat, positive, flat, negative, flat, positive. That's pretty much the graph that we have here, right? You see that it goes negative and then flat and then positive. That means it goes up and then flat and then it goes negative, flat. When I say it goes positive, I mean it's going up. The derivative is positive, not the value. The derivative is positive, so it starts going up, 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 up. Okay? Whenever we have this changing sign, I wanted to mention that, we have maxima and minima, not just that the derivative is 0. F prime has to change sign. Otherwise, we don't get a maximum or a minimum. If it just hits 0, if it just goes flat, but then it keeps doing what it was doing before, it's going up and then flat and then up again, that's not a minimum or a maximum. Or if it's going down and then flat and then down again, that's neither a minimum nor a maximum. So we're going to have a relative min at x equals -1 and x equals +1. We can find out what those values are by plugging them into the original equation. And if we do that, I believe we're going to get 2 minus 4, which is -2. Since we have a symmetry, if we plug in 1, we will also get -2. And then we have a relative maximum right here when the derivative goes from positive to negative, not negative to positive. So that's going to be at x equals 0. And we already know that y equals 0 there. So it's 0, 0. All right, so that means these little bumpies that go down, apparently this is at -2. -1 comma -2 and +1 comma -2. Okay, that's part A. Let's look at part B. Part B says find the coordinates of the point of inflection. Okay, so now what do we do with point of inflection? For point of inflection, we want to see when is the second derivative changing sign. So again, we're looking for when this derivative of the derivative changes sign. So let's go ahead and find out what the second derivative is. It's very similar to maximums and minimums, but we're doing it with the second derivative. The second derivative is going to be 24x squared minus 8. Okay, so we can factor this. 8 and 3x squared minus 1. If we want that to equal to 0, let's factor this even further. Square root of 3x minus 1 and square root of 3 times x plus 1. We can put this on our chart. And of course, as far as x values, we're going to get x equals plus or minus 1 over root 3, which you could also call plus or minus square root of 1/3, or you can call plus or minus root 3 over 3. Those are all the same value. It doesn't matter which one of them you use, really. Let's put these on a chart. So of course 8 is always a positive factor. Square root of 3x minus 1 is a factor. Square root of 3x plus 1 is a factor. And I'm taking my time to graph all of this out for you guys. I probably wouldn't do this so slowly and so cleanly if I were actually taking the exam. So we're going to have 1 over root 3, and we're going to have negative 1 over root 3. This one's going to make that 0, this is going to make that 0. And so overall, the second derivative is 0 whenever any of its factors are 0. 8 is always positive, and for these factors, we're positive whenever we're to the right of the zeros. And now we just sort of multiply all these things. So we're going to have positive, negative, positive. Now it doesn't really matter whether it goes positive to negative or negative to positive. We're just looking for sign changes. We don't distinguish the points of inflection like we do with maxima and minima. It's not as important. So this is going to be point of inflection there. You could say so POI at x equals negative square root of 1/3, and there's a reason why I'm writing it like that, just feel like it, and x equals positive 1/3. Now when we plug those in, it's actually not too bad. We plug them into the original function, and the reason why it's not so bad is because we have even powers, so the square of negative square root 1/3 is just going to be positive 1/3, but then when we square that, we're going to get positive 1/9. So this is like square root of 1/3 squared, and then we have square root of 1/3 to the 4th. Those are the two objects that we need when we plug these in. So we're going to have 2 times 1/9 minus 4 times 1/3. We might want to call that in ninths, so we're going to say 12 ninths for a total of negative 10 ninths. So that's the point that's associated with negative square root of 1/3. Okay, negative 10 over 9. Let's just double check that that's correct. Yeah, looks good. 2 over 9, 4 over 3, multiply 3 on top and bottom. Alright, well, because of the symmetry, we're going to have the same exact y value for this positive x value. So those are my critical points. Okay, and I know I use the chart, which takes a little bit of time to analyze, so you might be wondering, wow, do we have to do this on every single problem? Well, not really, because in fact the chart is going to reveal more than just those 0 points. It shows the positive and negative behavior. So C and D are going to be a cakewalk. It says determine the intervals on which the function is increasing. We just need to be able to interpret what that means. Increasing means f prime is greater than 0, which we can just check the chart for when it's positive. We see from the chart that it's positive between negative 1 and 0 and after positive 1. Let's confirm that on the graph. So between negative 1 and 0 on the x, it is going up. I can confirm the derivative is positive. And then after x equals 1, I can confirm it's going upwards again to infinity and beyond. So those look like good intervals. This is going to be from negative 1 to 0, union from 1 to infinity. So that is already answered. Very easy. Do the same thing for part D, and we're done. Determine the intervals on which the function is concave up. Now that's going to require us to say the second derivative is positive. That's what concave up means. And this is going to happen whenever the second derivative is positive, which we see is up until negative square root of 1/3, and then after positive square root of 1/3. So it starts off kind of happy face shaped, then it goes sad face shaped in the middle, then it goes happy face shaped again. Let's make sure that is valid. Yeah, it looks like this thing is happy face shaped until this point where it sort of flips over, and then we get another happy face part. Something like that. So this is going to be valid on the interval from negative infinity to negative square root of 1/3, union everything past square root of 1/3. Yeah, that'll do it. Okay, so very standard polynomial to work with here. Definitely was not anything taxing when we were doing the derivative. The factoring situation, I want to explain that a little bit, because now that we're in calculus, we're not just looking for difference of squares with perfect squares. Here we're able to see that x squared minus 2 could still be thought of as a difference of squares, because 2 is kind of like the square root of 2 squared. So if you think about it like that, a minus b, a plus b, then that's just going to turn into x minus root 2, x plus root 2. See that? I also did something similar later on here when I analyzed the second derivative. This doesn't look like your typical difference of squares, but in order to turn it into linear factors, we're just going to treat it as a difference of squares. We're going to say this is like square root of 3 times x squared minus 1 squared. So that's why we get square root of 3 times x minus 1 and square root of 3 times x plus 1. Okay, so in calculus, we're going to be using this factoring idea, even if we don't have the most ideal situation. It's about doing this conceptually and using a proper system or process, regardless of what the numbers are. You should be able to do the same calculus with, fraction coefficients or decimal coefficients. Shouldn't change much. Okay. And of course, the chart is all powerful because it gives us lots of information about either the derivative or the second derivative or even the original function if we wanted to. Okay, I think that's enough blab out of me. Continue watching the rest of the problems in this practice standards series, and you'll improve your skills hopefully in time for this AP exam, which is coming up pretty soon. That'll do it for me. I'll see you guys next time in the void.